Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at L-Tri-C. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. Today we'll be reviewing fission and fusion as part of our nuclear chemistry review. In this first slide here, we do a quick review of the basics of nuclear chemistry. If you remember, chemical reactions involve the valence electrons of elements. The nucleus does not get involved. It's just the electrons in the outer shell of the atoms. However, in nuclear reactions, the nuclei do get involved in the reactions, and that's why they're called nuclear reactions. Now, the types of nuclear reactions, there's radioactive decay, when a nucleus spontaneously breaks down and emits radiation, and we have a separate video done on that, and also a separate video on half-life, which is involved in radioactive decay. But in today's video, we're going to talk about fission reactions. That's when a nucleus splits into two smaller nuclei. And a subset of that is a chain reaction may result if the products of that fission goes on further and causes more fission reactions. And we'll review that today too. And then fusion, the other reaction is when two small nuclei combine to form a larger nucleus. So if we look here at fission, a nucleus splits into two smaller nuclei. What we show here is an example using uranium-235, and this is what is occurring in an atomic bomb explosion. You have uranium-235 and you hit it with a neutron. When that happens, you make an unstable 236 uranium, unstable. And that material then will quickly fission or break into two, into krypton and barium, and release three more neutrons. Now, this occurs 82% of the time. This fission occurs. 18% of the time, though, this unstable U-236 emits a gamma radiation, which is strictly energy, and forms uranium-236 stable, a stable form of 236. But as I show here, 82% of the time, it actually this unstable uranium undergoes fission, breaks into krypton and barium, and if you do just a gross mass balance here, you started with 236 total mass number, 91 here, 142 here, and 3 here with the neutrons. You'll see that adds up to 236. It shows a balance. What actually happens if you do a very accurate measurement of the mass, though, there is a tiny amount of mass that is converted into energy. There is some mass loss, and that's where you get, Einstein's equation, m equals mc squared. C is the speed of light, and that little bit of mass you convert over into energy gives you a lot of energy. And this fission reaction with uranium-235, essentially, if you can react 1 gram of U-235, that's equivalent to 3 tons of coal being burned. So you get a lot of energy, even though it's a minute amount of mass is being converted to energy. Because of that, E equals mc squared, you get a huge amount of energy. So this is what's happening in your atomic bomb, and what we'll show you in the next slide is the chain reaction that also occurs, so that you don't just get one fission here, you get compounded, you'll see, as a chain reaction, and you get more and more fission, and therefore more and more energy. Now in fusion, Now instead of splitting a nucleus apart, you're combining nuclei together. And this is what occurs essentially in the sun, what we showed down here. Hydrogen, you have two hydrogen atoms here. And if you notice, normal hydrogen, normal stable hydrogen, is just one proton. So a total mass number of 1, a atomic number of 1, and it has also 1 electron. But when you combine in the sun, when you start with a star, the gravity pushes together all the hydrogen and compresses it. You get high temperatures. And what you form is these other two isotopes of hydrogen eventually as your temperature increases. This is the one with 3 mass number is tritium, and then with the 2 mass number is protium. When you get these two isotopes and enough energy to form that, enough heat to form those, and then even more heat so that they can fuse together, you can make helium. And you also get a release of a neutron when this happens. But again, though it looks like there's an overall balance of mass here from products and reactants, there's again a slight amount of energy being mass being converted to energy again with the E equals mc squared. And I don't have the equivalent here of when this occurs how much coal is equivalent to a gram, but there's even more energy here in a fusion reaction than there is in the fission reaction of uranium-235. And that's why you've heard that industry is trying to come up with a fusion reaction as an energy source because it's even more economical. So that's what's happening in fusion. So just to finish up, I want to show how this in the fission reaction you can get a chain reaction, and how in this case here, if you start with a uranium atom, you hit it with a neutron, you get your fission products here. You get 2 fission products. You're going to get some krypton, and you're going to get your barium. But you'll also remember from this equation here, you're going to get 3 neutrons. 3 more neutrons. These are N zeros. Those 3 neutrons, as long as there's excess uranium around, they're going to hit 3 more, or can hit 3 more uranium atoms. Again, it can cause 82% of the time will cause fission, break up again into your krypton and barium, and then each one of those reactions are going to give you 3 more neutrons. And you can see, as long as there's excess uranium around, you're just going to compound your fission reactions in the energy result. So it compounds because your 1 neutron bombardment is resulting in 3 more neutrons, which can then go on. So that's how a chain reaction goes, and it will continue as long as there's a significant amount of excess uranium-235 around, and once that's finally depleted, then the reaction will stop. So that's the review today of fission and fusion. Thank you.